Hi, I'm Tom, W8JI. This video is about the 811A tube and the history of the 811A tube. Tubes went through a long development history starting in the early 1900s. The 811A tube fits someplace in the middle of this stream of tube evolution from the early, almost light bulb-like vacuum tubes through the World War II era and on up through the modern ceramic tubes. Over the years, we've developed an awful lot of different types of tubes for specialized purposes, from very small tubes to very unique tubes that are either cooled or ruggedized in a certain way to fit specific applications. The 811 type tube is someplace in the lower end of all of this evolution. The 811A tube is a kind of an old tube that really started to be developed around World War II. And it has a thoriated tungsten emitter, the filament of the tube, that forms an electron cloud. And then there's a screen of wire that is between the cathode, between the filament cathode and the anode of the tube. And so the anode tries to pull electrons from the cloud that forms around the heated filament wires. It tries to pull this cloud of electrons through the control grid. And as we charge the control grid either negative or positive with respect to the electron cloud that's around the filament, we can control the current reaching the anode of the tube. That's basically how the vacuum tube functions. We can think of the tube as nothing much more than just a time varying resistance, and it's just kind of a real loose resistance. It doesn't behave exactly like a normal little carbon resistor or something might behave, because it is a little bit imperfect. But nonetheless, by varying the voltage on the control grid as it relates to this cloud of electrons around the filament, we can control how many electrons reach the anode, and effectively we can control the resistance of the path between the filament and the anode of the tube. Ideally, what we want is we don't want very many of these electrons to hit the grid wires in the tube. It's the kinetic energy of the electrons in the tube as they strike the control grid or they strike the anode that causes a lot of the problems in the tube. It causes the energy from the electrons striking the control grid or the anode cause localized heating. And as a matter of fact, it's almost like a resistor. If we simply multiplied the voltage, the potential difference between the filament of the tube and the anode of the tube times the current flowing through that path, the heat in the anode is simply the product of the voltage times the current. This is integrated over time as if we looked at little tiny slices of the dissipation of the number of electrons and the voltage between the filament and the anode, and we integrated this into just one big number, that would be the actual operating dissipation of the tube. The filament structure in the 811 tube and the 572B tube are virtually identical. That's also the same as the 812 tube. There has been a change lately that kind of bothers me, and that is the Chinese have started to coat the filament of the tube with an oxide. This is a little bit unusual in a thoriated tungsten filament. It bothers me. While it increases the emission, it's real easy to poison an oxide layer. So a lot of 572Bs now seem to have really short filament emission life, And I think it has to maybe do with these little material changes that have gone on in the filament of the tube. But nonetheless, this filament that's pictured here is heated almost white hot, and that's what generates a cloud of electrons that we use for emission in the tube. Let's look at the control grid again quickly before we move on to the anode. If we look at this, it's just a screen of wires. Everybody complains about the control grid current and tube life and the drive power and this and that. These control grids and thoriated tungsten tubes are pretty tough. You can get the control grid almost up to incandescence, and the grid will still recover. So it isn't like a little bit of extra grid current is going to eat the tubes up. The big problem in the 811 tube is the anode of the tube. It's overheating the anode, and then you boil material off the anode and it contaminates the rest of the tube. Now understand, I'm not saying that you should run all the grid current you want to run. There's a certain level, like in 811 amplifiers, that the grid current is about 50 milliamps per tube, so about 200 milliamps overall, and it depends on the particular batch of tube that you get. But someplace around that level, the tube will operate at peak efficiency, and the intermodulation products won't be too bad on the output. You want to watch that grid current and not let it get too high, not necessarily because you're going to eat the tube up, but it makes the voltage in the tank circuit higher, and it also makes you splatter a lot. So it's being a good neighbor on the ham bands, and it's also maybe helping prevent an arc band switch or an arc plate tuning capacitor by watching that grid current and not letting it get too high on peaks. Now, a little shameless plug here. I sell a module that can go in amplifiers and let you watch the peak grid current. So you know all the time on single sideband or whatever mode you're on, you know exactly what the peak grid current is rather than the average grid current. Now the 811 tube is pretty much based off the old 812 tube. As a matter of fact, the early 811 prior to the 811A was really nothing but an 812 tube with a little bit finer mesh grid inserted in the tube. This increased the mu of the tube, and it allowed the tube to have a lot more gain when it was used in grounded grid. It also made the tube closer to a zero bias tube. So the denser control grid in the 812, making it an 811, had a lot of positive benefits for using the tube in class AB2 amplifiers, in particular in RF amplifiers that were grounded grid. If we look at the anode of the 812 tube in the picture here, we see that the anode is just a real thin, flat plate. It has a gray coating on it, like all of them do, and that gray coating helps getter the tube. It's a little powder that helps getter the tube. You don't have to heat these tubes, and you really don't want to heat these tubes as hot as you do like a 3-500Z. But they still do a little bit of gettering off the anode of the tube, and it's a catalyst. And like any catalyst, it likes to operate a little bit more at a high temperature. So it doesn't hurt to have a little heat on the anode of the tube, but you really don't want to run these tubes very far into the red region. So to increase the dissipation in the 812 tube and the anode from the 812 as it made it into the regular 811 tube, RCA and other companies started to weld metal fins on the anode of the tube. They welded crosswise across the anode of the tube. This ruggedized anode did a couple things. The overall dissipation of the anode over a long period of time really didn't go up that much. It increased, several watts. But what really happened is all this extra metal mass that they put there, all this extra mass added thermal mass to the tube. So you could overload the anode. You could have a pretty high dissipation in the anode, and as long as the time average dissipation stayed below 65 or 70 watts, someplace in that area, 80 watts, as long as it stayed below that level, you wouldn't damage the anode of the tube. So they could conservatively rate the anode of the tube at 65 watts, but at the same time you could have a peak dissipation in the tube. As long as you watch the duty cycle of the tube, you could dissipate 150 or 200 watts, or you could dissipate 300 watts in the tube, as long as the time average dissipation was low enough that the tube could get rid of the heat and not cause physical damage to the anode of the tube. Well, the Chinese figured out a way to make the tube a little bit different than we made the 811 tube here in the United States. The upper tube in this picture is a Joint Army-Navy 811A tube. It's a regular JAN tube, and the structure pictured at the bottom is the Chinese 811 tube. And you notice what they've done here with the tube is they've instead of using the little fins that run crosswise on the anode and make the anode look a little bit thicker, these fins are spot welded to the anode. What they did is they just bent the anode so the anode has two big fins that run vertically up and down the anode. And so they don't really increase the thermal mass of the anode, so you have a lot less, really you have the same dissipation over a long period of time. It's roughly the same dissipation. What you lose in this is you lose some of the thermal lag caused by welding these little channels across the anode crosswise. So the result of this is you can't run the high dissipation in these Chinese tubes that you can run in the old JAN type tubes that we made here in the United States. There also are some other structural changes in the tube that have an effect on the stability of the tube and the repeatability of the tube. One of the changes is if you look at the tube, one of the basic operating problems with the 811 tube is the long control grid lead. It's to get from the control grid of the tube down to the base of the tube, it's about 2¼ inches, and that 2¼ inches is a long, thin wire that runs all the way down to a single pin. And then of course you have to get from that single pin over to the chassis, which forms the ground plane in the amplifier. You want to keep that control grid lead from the control grid all the way down to the chassis of the amplifier as short and as direct and as solid a connection as you can possibly get. You don't want capacitors in that lead. You don't want inductors in that lead. You don't want resistors in that lead, and you certainly don't want a big long wire running around on the chassis to ground the control grid. You want that control grid to go right straight to the chassis with the shortest possible lead that you can get. What they did with the Chinese tube is they've moved the whole structure up a little bit. So they moved it about 1/4 inch. That doesn't sound like much, but it still adds unnecessary length to the control grid. And so they moved the whole, if you look at these two tubes, the base is sitting at exactly the same height. The anode caps are sitting at the same height, but they moved the whole structure inside the tube up higher, and they also use a thinner single wire lead to the anode of the tube, where the old JAN tube used a hoop that went across from one side of the anode to the other, and then they welded a short anode connector anode lead that went up into the anode connector through the glass, and this gave them a much wider and shorter path. So the old JAN tube was a little bit easier to stabilize. Okay, now I've done some measurements on these old tubes. I've destroyed a few of the old JAN tubes, which is kind of a shame to do. But the old JAN tubes, if you run about 130 watts dissipation on the tube, you can cycle the tube 10 seconds on and 10 seconds off. You wind up with about 65 watts of average dissipation, and you can do that on a tube 24 hours a day, and the tube lives just fine. If you increase the if you decrease the dissipation to 90 watts, then you can run the tube with 70 seconds on and about 30 seconds off. So the permissible transmit duration, the permissible time that you can actually be transmitting and dissipating fairly high power in the anode, really depends on the duty cycle and how much dissipation you have in the anode. So you can go over the 65 watts, but as you start getting up into the 130 or 140 watt range, you have to, the period of on to off time, the on time has to get progressively shorter and the off time has to get longer. Alright, if we look at the newer anodes in the Chinese 811A tubes, we now see that we don't have because we don't have the thickness in the anode. They've bent the anode out instead of welding cross fins across the anode. We see that the thermal inertia in the anode is a lot less, so we have to watch the on time a lot more at real high dissipations. We don't have the we don't have the thermal lag there to let us get away with going real wild on dissipation for 10 or 15 seconds. We have to watch it when we get into really high dissipations, because the anode being so thin can heat real fast, although that great big wide tab that they run vertically down the anode increases the permissible duration at 60 or 65 watts of dissipation. That goes way up. So all our damage that we do to the 811s in the 811 amplifiers and other amplifiers where we use these Chinese tubes, or or even even the old JAN tubes, is caused by how long we dissipate power in the anode and how much power that is. It isn't the control grids. That's not the worry. The control grids are a worry for splatter or intermodulation, and they're a worry for tank circuit voltages. But the control grid current isn't what hurts the tube. What hurts the tube is the anode dissipation and getting the anode so hot that the anode actually starts to melt. When you overdo the anode and get the anode too hot, this is what the tube will start to look like. You'll see there's a silvered area where the Gettering coating that's put on the anode has actually burned off, and now you have just where the metal was heated right to the melting point, you have a big silver area there where the anode got real hot. And so all that stuff that you've burned off the anode is what ruins the tube. It moves around inside the tube, and who knows where it's going to land at. So it'll either cause the tube to short out, or it'll just simply get over on the filament of the tube, and then you'll lose emission in the tube. This is a big worry, how hot you get the anode. This is why the 811 amplifier, although you can make it better with some bias mods and some other mods, but this is why the 811 amplifier is not a good amplifier for AM. It's not a good amplifier for high duty cycle modes. When I designed the Ameritron 811 amplifiers, the target instruction to me was to build the amplifier as cheaply as I could build it, and they initially just wanted to use two 811 tubes in the amplifier. I I convinced them that the idea of using two 811 tubes was a pretty bad idea and that we should add a third tube to it. So we added a third tube, and then I pushed and got them to put a fourth tube in the amplifier. We had to neutralize the amplifier to make sure the amplifier was stable with the fourth tube. But that was the evolution of the Ameritron 811 amplifier. It's really designed to be a minimal cost single sideband and CW amplifier, and it probably does a pretty good job of that as long as it's built properly and as long as the people using the amplifier understand how to use the amplifier and how to tune the amplifier. Part of the procedure I use here when I import tubes, and I've partnered with the former vice president of MFJ, and he and I are now importing tubes for resale in the United States. Is we test all these tubes as they come in, and we select the best vendor and the best tubes, the most reliable tubes from the best vendor. We measure the peak emission on the tubes in an actual tube testing setup, and we also inspect the tubes visually for workmanship. So we hope to be offering a little bit better tube, and we're working on 572s to try to find a better 572 for people. So I appreciate everybody putting up with this video, and I hope that all of this helps people get longer life from their amplifiers and also understand a little bit more about how vacuum tubes work.